ODF might have. So that motivates very nicely the next class of technique I'm going to talk about, spherical deconvolution. So the kind of premise of these sorts of technique is to model the signal. Again, here I'm showing the signal as a function of direction, assuming one of these spherical acquisition schemes, although these methods don't rely on that. So the assumption then is that the signal is the convolution of the fibre ODF with the measurements that we would expect to get from a fibre with a particular known orientation. So we can write that convolution mathematically like this. But let's take so in this simple example here, we have a fibre ODF that's just got pretty much just two non-zero directions. So to get the full signal under this model then, we rotate the model for the signal with a fibre in a particular direction to each of these two directions, as shown here, sum them up, and that gives us the overall signal. So the idea in these techniques then is to unravel this convolution to get at this fibre ODF, which I'm calling F in this equation here. And there are some standard ways to do this kind of deconvolution, and in fact with the simplest sorts of implementation, it simply boils down to just a simple matrix multiplication. A kind of criticism of the early implementations of this kind of technique was they were quite sensitive to noise. So sort of future developments of those techniques have built in regularization and various constraints into this deconvolution. There's a whole list of different techniques here. I'm showing a result from the recent, I think this is yours, isn't it, Donald? I think so. This is showing that actually these recent techniques, now that these regularization and constraints have stabilized the technique, they're starting to show some really nice results. So finally, the pass-MRI technique. So this kind of sits somewhere in between these two previous classes. The original implementation estimated a function a little bit like the diffusion ODF from diffusion spectrum imaging, in as much as it is a property of the particle movement rather than directly an estimate of the fibre ODF, but designed to reflect the fibre ODF a bit more directly than the diffusion ODF. And then later work on this kind of generalized it to encompass a similar idea to spherical deconvolution, where we use a model in the technique to get more directly to the fibre ODF. I won't go through the details of the technique, but I'll just point out the one unique feature of it, which is that unlike the previous techniques I've mentioned that tend to use linear basis representations of the output of the procedure, so things like spherical harmonics or radial basis functions to represent the diffusion or fibre ODF, this has a non-linear and in some sense optimal representation for that output. One of the problems with the linear bases is that they tend to be very smooth functions, whereas true fibre ODFs can be extremely spiky functions. If you imagine the true fibre ODF in a big white matter motorway, most things are pointing in the same direction, so the fibre ODF is not far from a delta function. So the idea of this non-linear representation is that it much more naturally captures these very spiky functions. So I'll just show you some output from this method. So if we zoom in a bit to some interesting regions, we'll see very little in this region from diffusion tensor imaging, but this technique reveals much more angular structure. And you can see that we can capture these very spiky fibre ODFs in regions of coherent white matter. One more example here, consistently recovering fibre, crossing fibre orientations. So those are the broad techniques I was going to talk about. As I said, all sorts of other things out there in the literature. Very briefly, some of the more popular ones. Spherical harmonic cubal replaces Dave Tuck's original radial basis function representation of the diffusion ODF with spherical harmonics, which are a bit more economical and elegant in some ways. The diffusion orientation transform, again, similar in spirit to DSI and cubal in that it estimates a function of particle displacements. Higher order tensors and generalized DTI give us another representation for these orientational functions. Hybrid diffusion imaging, nice elegant way to generalize diffusion spectrum imaging to more general sets of samples, so not limited to this grid sampling that they originally used. And diffusion kurtosis imaging, which Donald talked about in some detail, looks at something slightly different as a function of orientation. This so broadly captures the amount of restriction or non-Gaussianness as a function of orientation. So let me just emphasize again, oh no, sorry, that's not what I was going to say on this slide. Broadly, we can distinguish all of these different methods with three different features of them. The first is the object that they compute. So do they compute the fibre ODF, the diffusion ODF, or one of these other objects? What's the representation that they use for that object? Do they use spherical harmonics, or one of these other linear bases, or some specially tailored non-linear basis? And what's the acquisition protocol that gives the measurements from which to estimate that object? Do they require a grid sampling, a single sphere, or multiple shells, or some sort of random sampling? So these other things are becoming more popular recently.